if you can get out your table of friends, what we're going to kind of do here is we're going to add to the table of friends, kind of review as we do so, and then probably add some things over here as a review to that didn't quite make the table of friends. We have 3 new friends today. Please give me someone to add to our table of friends. Sergey.
Howard.
Power is going to be the 3rd that we're going to add here. So Power. Let's get all 3 friends up here so we know what we're working with. Silva. Work is the first one. And the one in the middle. We have work, power, and between them, Siddiqui?
Oh, is it potential energy?
We're just going to actually put energy. It's just going to be one category for energy. We'll talk about the different types of energy as we get through here. Let's start with the symbol for work. Dorstetter. W. I know some of them are complicated. The dimensions for work. Mohit.
Joules.
Joules. What is a joule, Meg?
Newton meter per second.
Ah, just Newton meter. A joule is a Newton meter. And what is a Newton? Stacey. Yeah, in base SI dimensions. Kilograms, meters per second squared. The equation, we have 2 different equations for work. Please give me one of them and under what circumstances you would use that equation. Kathy?
Work equals force times delta R times cosine theta.
I'm going to put the dot product. It's certainly F delta R cosine theta, but I'm going to put the dot product or scalar product. And under what circumstances would you use that one?
Which is a constant force.
This is for a constant force. We have another equation for work. What is that equation? Tyler.
Oh, work equals the integral from xi to xf.
What do I and F stand for?
Initial and final position.
Good.
Of fx force x times dx.
Or rather than times dx, it's with respect to x, right? This is the integral of the force with respect to position. Under what circumstances do you use this equation? Bill?
When you want the work from a certain kind, like the initial.
No, there's a.
When there's no constant force, right?
When the force is not constant. When the force is not constant. Okay. The symbol I'm going to put down for energy is the U, because that is a newer symbol. You're probably less familiar with that. What are the dimensions for energy, Eugen? Help him out, Potterella? Wow. Yes, this is one of the more complicated questions. Winter? Mohit?
Joules.
Joules? Work and energy are the same dimensions, so it would be Newton meters. We have several equations for energy. We're going to do the 3 types of mechanical energy. Tell me the type of mechanical energy and the equation for it. Tim?
There's energy, so that's 1/2 mv squared.
1/2 mv squared. 2 other types of mechanical energy. Travis, give me one.
Potential energy, gravitational.
That I'm going to put U sub G for gravitational potential energy equals?
MGH.
MGH. So kinetic energy 1/2 mv squared, 1/2 times the mass times velocity squared. Gravitational potential energy MGH, where m is the mass, g is the acceleration due to gravity here on planet Earth, 9.8 meters per second squared. What is H? Zach?
From 0 on.
Remember, in order to talk about gravitational potential energy, you need to set the 0 line. The last type of mechanical energy, Emily?
Elastic potential energy.
U sub E, which is?
1/2 kx squared.
1/2 kx squared. K is what? Vlad?
The displacement from the equilibrium position.
That was the answer to what
my bad. That's X. K is
That is X. Okay, hold on. So we'll try this again. Vlad, what's X?
the displacement from the equilibrium position.
Good. That is the displacement from the equilibrium position. The equilibrium position is also called what, Hillary? Another name for the equilibrium position. I want to give you both because sometimes you'll see it either way. Help her out. The equilibrium position, Dorsetter. Also sometimes called the rest position. What is K? We'll try this question, Loki.
The constant, spring constant.
The spring constant. Henry, what generally are the dimensions for the spring constant?
Newtons per meter.
Newtons per meter. Power. What is the symbol for power, Gary? Uppercase or lowercase?
Uppercase.
Which one?
Uppercase.
It is uppercase. Lower. What is the symbol? What is the lowercase p the symbol for?
Momentum.
Momentum. Density is a rho. Sorry, there's three different rows. The dimensions for power. Dimensions for power. Emily? Watts. What is a watt, Nitish?
Joules per second.
Joules per second. It is the rate at which energy is consumed, or it depends on exactly what you're talking about. We have a couple of equations for power. Please give me one of the equations match. Power equals.
Just FV cosine theta.
That is one. I'll put it all the way. I'm going to put it over here. F dot V. We're going to get there. We have a couple things to put in between. That's okay. Bill?
Work over time.
Work over time. As such, what type of power is this, Nick? This is not, the net power would simply be, because you talk about the net power, the power delivered by the force applied, that would just depend on which force you're talking about. That would give you the net power. This is the average power. We have the equation for the instantaneous power. Instantaneous power, the equation is what, Mill?
Derivative of work as a function of time.
Derivative of work as a function of time. And of course, we can have, that's also equal to FV cosine theta. I'll give a little bit more space there to put it in. That's equal to the derivative with respect to time of F delta R cosine theta, which is F dot V, because the derivative of the position as a function of time is velocity. That, I believe, adds everything to your table of friends. Let's highlight a few things that didn't quite make it to the table of friends. With the dot product, don't forget to be able to use the unit vectors, I, J, and K with your dot product. Those are very important. I went through mathematically how to do that in class. Some of you had forgotten. You might want to review. The derivative is the slope of the line at a point. What is the integral? What is the integral, Mr. P?
The area under the curve.
Good. You put quotes on under. What do the quotes on the under the curve mean? Nitish.
It's between 0 and like 2 points.
It's between the whatever on the x-axis and your curve. With one other thing I wanted to make sure people remember. Went through an example, Nick.
Below the curve is negative.
Remember, the area below the curve is negative. So the area under the curve simply means the area between the curve and the time axis or x-axis, depending, and where the area below that x-axis is negative. We have an equation for the force of a spring. What is the equation for the force of a spring, Jenkins? Negative kx. We've already talked about k and x. What is this negative in this equation mean?
This is the opposite direction of
The force of the spring is opposite the direction of the displacement. Remember, if you've drawn your free body diagram and some of the forces, you've already used that negative, so you would use the magnitude of the force of the spring. We had 3 different equations for work. I want to know what they are. Actually, I'm sorry, 3 different equations that related work and energy. I want to know what they are and under what circumstances you can use them. Please give me 1. Sierra.
Net work equals change in kinetic energy.
Network equals change in kinetic energy. When can you use that one?
When there's no friction or there's a force applied.
Sorry, that's not correct. Although you can use it then. Emily.
Always.
You can always use this one. This is the one we can always use. We have 2 more involving work and or energy. Ponderella.
Work due to friction is equal to change in kinetic energy.
The work due to friction equals the change in mechanical energy. These are the 2 that often get confused, and you can see why. When is this one true? Priscilla.
There's not a force applied.
When there's no force applied. We have 1 more. What is that equation, please? Hamza?
Mechanical energy initial equals mechanical energy final.
When is this one true?
When there's no friction or force applied.
No force of friction and no force applied. Great. We've done all of those. We had, bless you, an equation that is not on your equation sheet and is true for all conservative forces. I told you need to have it memorized. I need to know what that equation is, please. John.
Can you repeat that?
Sure. There is an equation that is true for all conservative forces. It's not on your equation sheet. We talked about it. I showed examples. I said you need to make sure you have this equation memorized. Help them out.
Fx equals negative derivative of potential energy over x.
The force, the conservative force we're talking about, is equal to the negative of the derivative of the potential energy associated with that force with respect to position. Please remember that you can always rearrange any derivative into an integral. In other words, and we already went through this, this is equal to the change in energy is equal to the negative of the integral from the initial to the final positions of the force in the x direction with respect to position.